Live controls. All right, today we're going to talk about some more things you can do for design optimization, setting up designs, performing analysis in SolidWorks. We're going to talk today about doing analysis in assemblies and some of the limitations and advantages you can do there. We'll also talk about some tips that you can use to help make assemblies faster. And I'm not sure again exactly how much we're going to get through today, but next week we're going to be going into more detail on parametric and non-parametric design. So using design optimization with parameters you've explicitly set versus saying, hey, SolidWorks, just use your FEA analysis to give me a good geometry with whatever these boundary conditions are. I generally don't like the non-parametric designs. I'm getting way ahead of myself because it's next week's topics, but they can give you a good idea of what the general shape of an object should be if the loading conditions are well known. So to get started, go ahead and download this robotparts.zip from Canvas. Is that door lock? Is the door lock?
Yeah.
I see like those about unlocking it. So it's already unlocked. So with that zip file downloaded, go ahead and open up the zip file. I'm going to drop that into a folder on my desktop. So I'm just going to go to week 4. Yeah, robot parts. I don't want to use it I don't want to do it in the same folder as I have these other parts. So I'm just making a new one. Let's call it robot. These parts are actually not going to let us build a complete robot, but there are some more components we can use to demonstrate some of the tips that I want you guys to look at for assembly processes. After you've got that downloaded, I've already opened up SolidWorks, but if you haven't done open SolidWorks, go ahead and do that. I'm going to start with a new assembly. I'm going to go new and then assembly, then OK. Waiting for that to load. For the first component that I'm going to put into here is I'm actually going to use one of the arms. So I'm going to go into my folder I just made. Click on robot arm. Click open. And then as usual, I'm just going to click on the green check mark to place that arbitrarily, or really to place it non-arbitrarily, so the origin is aligned on my workspace. My goal with this design is actually to evaluate a generic robot arm that will have a motor on one end and a coupling on the other end, and I can put them together in a series of connections to make a robot that is as long and as complex as I want it to be. Every joint will be at 90 degrees from the previous joint. So if I put 3 of these together, I can actually get kind of any position I want in a fairly restricted volume because the arms are all the same length. But it will work reasonably well. If I put 4 of them together, then I have a little bit of redundancy in position, which I can use control for orientation. If I put 6 of them together, I can control position and orientation independently. And I also get a much larger workspace. But it's a fairly decent starting platform for a robot if you wanted to build that out. You could also replace this with a humerus or a femur and do a fairly similar analysis, although the contacts on the joints there are much more complicated. And so that gets harder from a simulation standpoint. I want to be able to make this modular, and to that effect, I want the start of one part to really be the end of the next one. So I'm going to try and build my assembly that I can make this a sub-assembly and then link them together to make more and more longer robots from that standpoint. I'm just telling you guys all this from the start, so as we're building this, it makes sense to you as we go through. So I'm going to need a bunch of pins. I'm going to need a motor, and I'm going to need a, I forget what I called it. They called it a bracket. And I'm also going to need the shaft for the motor. So I only need one of the motor, the bracket, and the shaft. So I'm going to drag all three of those in. Try and drag them in. Come on now. I probably should have dragged them in one at a time. I've mentioned this before. I usually drag things in one at a time because dragging all three at the same time can cause issues in SolidWorks. Yeah, we're okay. What I'm going to do is I'm going to put this bracket on the base. I'm going to call this first side. The two sides are actually identical. They're just rotating 90 degrees from each other. And then I'll put the motor on the other side with the shaft. The reason I have the shaft separate from the motor is that I want to be able to rotate this. Yeah. Wait, how many things? You need one of all of these four parts. So one of the arm, one of the bracket, one of the motor, and one of the shaft. So I'm going to mate these in their general position. So I'm going to use a concentric mate to put this bracket aligned with that hole there. I'm going to use concentric mates to align just one of the holes on these two sides so it can't rotate. Don't add additional mates. You can. I could add mates for every single combination of holes on here to make them all concentric. I don't need to. You generally don't want to add more mates than you need. I'm going to put the kind of the inside edge of that bracket onto the face of the arm. Good? All right, and then I'm going to take my motor on this side and I'm going to do largely the same thing. The motor, it doesn't matter how it's oriented because it is symmetric. The bracket, try and make sure that this set screw hole on the side is going out so you have access to it. Oh, I didn't mean to undo that one. I'm going to do the same thing on the other side. I'm going to get the center of the motor and make it concentric with the center of this hole. I'm going to take the face of the motor, make it coincident with the face on the arm, and then it can still rotate. So I'm just going to take one of these pinholes and make it concentric with this other hole. A few things I want to note in this design. I have made all of the holes for both the arm, the bracket, and the motor have a standard 6 millimeter diameter, even though I intend for one of those to be a clearance hole and one of them to be a threaded hole. The reason I'm doing that is because I can't really use the tapped hole size in my simulation, because if I try and put a fastener in there and there's interferences, it won't run the simulation. So the simulation does not want to model and render threads. We will control the kind of the condition of the thread with our bond types in the simulation. So whenever you're doing an assembly simulation, it's important to think about, do I need to modify these parts in a way that will make the computation on the computer side more effective, easier, whatever you want to call it. And then I want to make sure I have this shaft for the motor kind of in the motor. Oh, I forgot I'm not in mate anymore. So I'm going to click on the mate tool again. So I'll accept that. And I'm not quite sure how far I want that to stick out, but I'm going to add a distance mate. Have that stick out. Let's say 20 millimeters. That doesn't seem far enough. Let's say 40. That seems good. It's going to have to go into the bracket on the opposite side. Questions on any of those steps? So that's all using things that hopefully are well-known aspects to you all. So far, so good? All right. The next thing that I want to do is I want to add the pins in all of these positions. And one of the things you can do in an assembly to make things faster is use what's called the copy with mates tool inside the assembly. So I'm going to add one pin, define the mates for that pin, and then I'm just going to copy it and reassign the mates for all the different positions. And if I remember correctly, I think there's a hotkey that I can actually do multiple at the same time. So I'm going to bring in one pin. I'm going to mate that pin so that way it is concentric with the holes and that the face is flush on the inside of my part. It's going to stick out the back a little bit, which is fine with me. Totally okay. And that pin is going to be underdefined, but it's just going to be able to rotate in position, so I don't really care. You could by adding an additional mate, but since it's not going to change my simulation, I'm not going to bother with it. And it doesn't prevent it being able to rotate is not going to change the performance of the assembly in any way. So generally, if the rotation doesn't change the geometry, it's not worth adding the additional constraint. Every constraint you add to the assembly is a potential failure point when it tries to resolve all of the mates at the same time. So keep that in mind. Extra ones are definitely bad. So if I right click on here, you see this option copy with mates. Do you see that? So I'm going to click on that. This option is always a little bit confusing to me because almost all the time in SolidWorks, when you open a tool, to get the thing you want, you click on the green check button. In this case, you don't click on the green check button, at least not yet. I have these little option sliders over here on the right where it has the next and back buttons. To use this tool, I've selected the component that I want to use already, the pin. To actually use the tool, I need to go to the next option in the menu. So just be aware that some of the features in SolidWorks will have these kind of tabs you have to go through to get to all the different options. Whereas most of them, they just have more stuff down here in the workspace. So after clicking on copy with mates, again, I right clicked on the part, went down to copy with mates. You can also search the commands and look for copy with mates and then select on it, but that's the easier way to get to it. We go to next. Then I have this concentric here. So there's the concentric mate and there's the coincident mate. It highlights that mate on the current part. So if I click on this component there, it fills it in for that mate. Click on that one there, it fills in the next one. You notice it's made the part there. You see that? If I click on repeat, it's just going to use the same face as I used last time. So that can be faster because I can use that same face for all of them. Click on the one, accept that one. Click on the next one. Accept it. The next one, accept that. So since that one is using the same face for all four of those, that repeat option allows me to not have to reselect that face each time. So I got 4 pins. And then when I'm done, I can just click on the check mark to leave or the exit. Oh, I got an extra one because I clicked on accept and then didn't finish it. You get an extra one, just delete it. If you don't want to use all of the mates in the base part, in the derivative part, you don't have to. You can just use the ones you want to, and then the rest of them will just be underdefined. So if you have 100 mates on a part and you want to copy it with just 3 of them, that's totally okay. Make sense? I'm going to repeat that for the other side. So I'm going to start with one of these parts here. So click on it, right click, copy with mates. Go to the next option in the menu. Click on my parts here. I don't know if I can control click. I don't think I can. There is an option. There's an option somewhere that lets me do this a little bit faster to do multiple components at the same time. Do you remember what the hotkey for that is? Yeah, let me leave this for a second. It's frozen. I'm waiting for it to respond. So in the normal mate options, were you seeing the multiple mates?
So this with the lightning bolt.
Ah. And then you can just do concentric and click on multiple surfaces.
Like you highlight that face. You have to have 4 pins in there already, but then you can select all.
Oh, they're just applying the same mate multiple times. Yeah, yeah. Now there's a way of just saying that I want to copy this into all of these locations at the same time, which is like the fastest way of doing something like this. The other way that I like is you can use patterns. So this is obviously a circular pattern. I can just click on any circular object at the center of that pattern, click on my component, and say I want 4 of them with equal spacing. That's 5. That works fine too. Again, anything that you do that produces the same geometry is totally okay. You could also make a subassembly that had those 4 pins already in there. There's advantages and disadvantages to all those different things. As your assemblies become more and more complex, you're going to want to use subassemblies, patterns, even folders to group these things together, because they're going to get really complicated really fast. Questions on any of those techniques? All right, we're just going to make this a link subassembly, then we're going to make a new assembly that just has 3 links in it. So save this as in the same folder as your parts, link. And then we're going to make a new assembly. I can do make assembly from part assembly, make assembly from assembly. I like the sound of that. We're going to start with link. Yeah, that sounds good. Then I'm actually just going to copy this. So I'm going to click on link, hold Control, hit C, and then V. So I just copied and pasted, made 3 links. I'm going to move them apart. So I'm going to click on the move tool. And then that's not the one I want to move though. I want to move this guy. There you go. There's all 3. If you can't move something because it's inside something else, that's a neat trick that you can use. I'll show that one more time. Oop, I didn't do my copy. So I did Control C to copy from the model tree and then Control V twice to paste it in. If I click on the part and then click on the move option, I don't have to click the part. I can just click and then click anywhere and the selected component will move based off of what I have selected in the model tree. So if you're having a hard time clicking a part, especially if it's like a small part in a big assembly, you want to move it, you can do that. That can also be a good way of getting little parts out of complicated assemblies if you're trying to isolate them. Sometimes it's hard to get, say, a pin in the middle of one of the arms or something. You may want to fix that. Questions on that? Everyone's still following along? We've got 3 link subassemblies in an assembly. Not Pedro because he's having computer troubles. As link.assembly. Owen, you okay? Caitlin, good. All right, let's mate these together. So this is my first one, it's fixed. I'm just gonna leave it right there. My second one, I wanna put the bracket So that was on the output shaft of the previous robot. So I'll go to my mate tool, click on my bracket, click on the shaft. I don't want them to be nested inside each other, so I'm going to reverse the direction of that. That looks good. I'll accept that. I want to have some distance between these two, so I'm going to use a distance mate in these two adjacent faces. I don't want it to be very big, but probably more than 1 millimeter. Let's say 5 millimeters. Let's say 4. No, 2. 2 is fine. I do want that shaft to be far enough out that I can get it with a set screw. And what I'm going to do is I'm going to add another screw to this. So I'm going to add another pin. I'm going to put it into this mate right here, or into this bracket. In this case, I'm control clicking the parts before I select the mate, and that will automatically kind of pick which one it thinks is best. And I want the flat surface on that drive shaft to rest on that pin. And the way I have this set up now is that when I rotate this, I have to make my base link flexible. So that's one thing here. When I bring in a subassembly, the subassemblies are treated by default as being rigid. If you want the parts to be able to move within the subassembly in the main assembly, you have to make them flexible. So what I'm going to do is I'm going to right click on that guy. And there should be an option here where it says make flexible. So it's this little option right there. I thought there was a text version of that as well. I'm gonna try and get that to see make subassembly flexible. It's like a little Tetris piece with a box next to it. And then if I click it again, it just toggles. But now I should be able to rotate. And what's happening when I rotate it is that pin or the output shaft in the base assembly is being allowed to rotate. I could also make that connecting shaft part of the main assembly and not the subassembly. Then I could leave that whole subassembly as rigid. And there's advantages and disadvantages of doing that. But if you have a subassembly that you want to have motion, make sure you are aware of that option to make the subassembly flexible. The last one I actually don't care about. So on the second link, which I actually have in the wrong order, I'm gonna make it flexible. And then the last one I'm just gonna leave as rigid, because I'm not gonna have any motion there for what I'm gonna look at. I'm gonna go ahead and add the next set of mates. It's the same as I did last time. So mate. And I could have copied with mates if I really wanted to do that again, but you got to balance what you think is reasonable in terms of being able to keep track of what you're doing and the fastest way of doing things. And I need to add that last pin. So I'm going to bring in one more pin. So I can pin my coupler to the output shaft on that. If you can't see that output shaft, what I would suggest doing is leaving the mate tool temporarily, making it transparent. So there's the change transparency options. Now I can see the inside of it. And again, I can rotate that shaft because I've already made it flexible. And then I can go through and I can add the mates to those faces. And I'm control clicking to get both the faces, and then clicking on the mate option to add the mate. And you can see now I've got this robot. I can move it around different positions. play with it however I want. Fun stuff. The question I want to ask with my subassembly or with my assemblies is really, how does the weight of the robot impact the stresses inside the parts, and have I appropriately selected the right geometry and materials for the different links? And the way I'm going to do that is by applying gravity to the simulation, using that to calculate the stresses and components. And then I can also go back and I can change the position of the robot to get it in a position that's more or less stressful or has a different stress distribution, and then run it again. I want to decide how many components do I really want to analyze as part of this simulation. And that's one of the things you got to consider as part of the setup, because you can actually exclude components from the simulation in terms of not calculating their results. So let's start off with something simple. If you don't already have it turned on, go to your SolidWorks add-ins and turn on SolidWorks Simulation. You do need the full simulation package to be able to run simulations in assemblies. I'm going to do a new study. I am still going to do a static study. Under loads here, I have the option to add gravity. I'm going to see the gravity load there. So click on that. I have to note kind of what direction do I want to add gravity in. The hardest thing for this robot, if I consider this portion down here to be the base, if I have gravity going kind of perpendicular to this first length, that's what's gonna induce the most load into this robot. So if I put all of my arms going in one direction, so there's the largest possible distance, and then I have gravity going perpendicular to that length, that's going to be the most load. So I'm going to go ahead and keep the gravity going in this Y direction. So going actually in the negative Y direction. It's using Earth gravity 9.81, which makes sense. Have you guys seen the Canada arm on the International Space Station? Yeah, it's a really long tubular arm. It looks kind of like this. So I'm trying to model this after the Canada arm. I actually don't know what components they use in that. This one is using NEMA motors, probably not using off-the-shelf NEMA motors, although maybe it is. But it's also in space orbiting the Earth, so there's no gravity, right? Well, there is gravity, but it's counteracted by the fact of the constant linear or circular velocity change. Anyways, no weight. We're going to accept that. That's all I really care about on this, except for I need to make sure I have to always fix something. If I were to hit run on this, it would just accelerate up into space and it would say error, all the stuff moved too far, I gave up, the end. So what I'm gonna do is I'm gonna fix this back plate as if these pins were fixed. Keep in mind that I'm gonna pretend like this is being pinned to like a wall or something. So the pins themselves won't be able to move, but all the things attached to the pins can. So I'm going to take this guy right here. I'm going to fix it. So I'm going to go into my fixtures, fix geometry. And what I can do is I can actually fix the faces of all those pins. Just the sides. If I fix the sides, since there's nothing on the tops and bottoms, it's not going to make any difference. Now you may ask, okay, I could do that. I could also fix the pin holes inside my arm, but those will give you very different constraints, because what I'm going to do is I'm going to set up a bonding condition there. This will allow the holes to adjust a little bit around the pin, whereas if I fix just the holes, you have a little bit different dynamics there. So I'm going to accept that. I don't need to include this part in my analysis, so I'm going to right click on it. I can find it in the part tree here. I'm just going to say exclude from analysis. I probably need my other components. I'm going to put these into a position. They're all kind of straight out. That's going to be the worst possible condition for my system. And I'm going to set my global contact inside this system to being non-penetrating. So where we have all this stuff set up, this right now is currently modeling as being bonded. Actually, let's leave it as bonded and we'll run it. We'll see if this works first. And then if we can, we'll change it to non-penetrating. The bonded is always going to be the easiest condition to solve. Let's see if this will actually mesh and run. Always a good idea to check that before you go on too far into a simulation. Keep in mind, in this example, our goal is really just to see if the robot is strong enough to support itself. And this is going to be a function of the weight of the components, gravity, although gravity we don't have a lot of control over, and how strong they are. Saying we have excessive displacements, we can solve with large displacements turned on, or we can say no to solve with small displacements. I'm actually going to start off with saying no and having it solve with small displacements. The difference between large displacements and small displacements is when you run large displacements, it actually runs the simulation, measures how far it displaced, reapplies the loads and conditions, runs the simulation again, checks to see if it changed, and then runs it again and checks to see if it changed and runs it again. So if you're doing a first pass on an analysis and you haven't really resolved a lot of the design parameters, when it gives you that large displacement error, you probably want to start off with saying no. The only thing that's going to be wrong with that is that if you have a beam that's curving like that, and I say you have a force of 100 newtons, right? As it curves, that distance is no longer what it originally was. It actually gets shorter. If you say no, this beam can go like this infinitely that way, like with infinite shear, because it's just going to assume that that 100 newtons carries forward forever. Or if you have large displacements, it'll calculate how that changes as it bends. And so you get a much more realistic deformation profile. You'll note that on this one, the deformation scale is still only 1.7. So this is being shown at a slightly larger deformation than what actually occurred. And it's not like it's bending over sideways. So with these conditions, it's probably fine. Like we mentioned before, we can't really see what's going on in here because there's too much blue. Almost the entire model is blue. This is very common in a non-built for classroom kind of thing when you're running a simulation. But what we talked about last time is I can isolate the areas that are higher or lower than whatever value I want to see where the stress concentrations are much more easily. So in my stress analysis, I'm going to right click. I'm going to go to my ISO clipping. And then in this case here, this is my current value for the ISO clipping. And I can look and see on that, where is my values? Everything is lower than that value. There we go. All right, so I'm starting to see where some of those things are. There's my connecting pin, right? Nothing there. So under the stress results, this is after it's run, right click on that. And then you have ISO clipping. The ISO clipping basically says anything that is below, above or below a threshold, don't render it. And again, right now, if I'm looking at this, I don't see anything red, right? So without that ISO clipping, it's really hard for me to see what the heck is going on and what's causing an error. So I'm going to right click, chart options. Oh, sorry, wrong one. Right click, ISO clipping. And then I can move this slider around to see where my stresses are. Right? You can see that really what I'm seeing in here is that these things are fine. It's this first pin where the stress is being carried across that I'm having my stresses. If I go to my second pin, I got nothing. And even up here, I got nothing. Right? So there's my pin. It's not until I get down to around, I need to change my units. I'm gonna change my units real quick. I'm gonna do chart options. No, definition. I'm gonna use Newton millimeters. Megapascals is just a much nicer unit to use for engineering terms. And then I'm gonna do my ISO clipping again. There we go. So it's not until I get down to around 49 megapascals that I start to see issues outside of that pin. And even my clearance there, even though this is a deformed state, it's not bending so much that 1 millimeter clearance is being used up. Getting way different numbers than me. Is your gravity going in the same direction? Is your that's it. Direction of the pen. You're still getting the, the application the same value. So on this case, if I'm thinking about this material from a material standpoint, I can see that the stresses in the pin with this configuration are on the order of 200 megapascals, which is a ton, right? It's a lot. So I gotta look and see if I'm using a steel pin, what kind of pin would I have to use to be able to withstand that amount of force? Where's my pin? Not the pin, it's the NEMA shaft. Right now I have it as plain carbon steel just as a placeholder. And honestly, any steel that I pick is gonna not change my results significantly because it's not gonna change the mass of the system. It's just the yield strength that's gonna be different. So right now, this plain carbon steel pin has a tensile strength of 400 megapascals. So it would probably be okay. And I could swap that out for something that is, a little bit stronger, or I can even go to a tempered steel, right? Which is quite a bit stronger, has 1,000 megapascal strength. And honestly, your output shaft of your motor probably needs to be pretty strong, right? And in this case, I've not designed this very well because I have no bearings to support the loads and distribute them inside this robot. I don't know why, but I see that a lot in robots where they have the mechanical coupling is basically being held by the motor as opposed to some kind of thing that's going to distribute the force over a large area and then attaching the motor to that. I think they're just trying to save space and weight. At some point, if you can get your motors light enough, it doesn't matter anymore because your robot's so light, you can put all the force on that single output shaft and it's fine. Questions on that so far? Make sense? I want to talk a little bit about design optimization inside this kind of a system, but we're going to cover that in greater detail in future classes. On my ISO clipping, on this, I do note that when I get down to 40 megapascals, I start to see stresses in other components besides the pins cropping up. And if I want to see what the minimum stresses are in everything that's not that NEMA shaft, what I can do is I can hide, not suppress, but hide those components. So I'm going to go into my main assembly here, or my sub-assemblies. I should have put them in the main assembly, and I can hide that component. I don't think it'll automatically hide it in the other ones. It does not. There I've hidden all the shafts. And then if I hide and show the stress results, it will exclude the shaft from the stress results. And so that can make it easier for me to see where the stresses are in the other components, because now my slider is not quite as sensitive to positioning. And I can also do things like showing what the actual minimum values are and going from there. To use this in design study, what we do is we do new design study. You guys can see that on the bottom. But you can see on the bottom, I'll move it up a little bit. So if you right click down where it says static one, you can do a new design study. You typically want to have a simulation set up before you do the design study. Then in here, you can pick what you want to change. So in this case, if I wanted to change the length of this arm, I don't remember which extrude it is. That's the sketch. Oh, there we go. These are all referencing relative to each other, though. I'll probably change it inside here. Oh, I gotta save my assembly. Let's save it as robot. Save all. This is the actual length of the robot right here. No, hit apply. Parameter name is not defined. Oh. Gotta give it a name. And then I can go through and add constraints. The constraints are based off of sensors. I gotta exit the sketch. If I was doing a better job of playing this out, I would have made the length of the robot a global variable or something like that, and I could have pulled that in much more easily. Then I can add my sensors. Usually their sensors are something like the stress inside the part, which is pretty common. So you can change this to simulation data. You have to have a simulation to be able to do that. And there's stress, von Mises stress, properties, with the different values we have. And we could say that we want that to be under a certain value. So I'm going to add that sensor. And I don't know why I chose PSI. Let's say 1000 PSI. This static one here is the study you're pulling that data from. And then your goal can be to minimize mass or maximize length. I'm going to say the mass properties, mass, okay. I'm actually going to say to maximize the mass. So maximizing the mass by changing the length will make it as long as possible. We don't have enough time to really go into this in detail. I do want to make an explicit point that right now, I'm not setting these values, but you'll notice that it goes from 250 to 750. It's currently 500 and a step size of 250. That step size is too big because it's only giving me 3 steps. So I'm going to change that to 100. Also, if I think that this one already works at 500, I probably don't want to start at 250. So if 500 already works, use that as your base standpoint. I don't actually know if it works for this simulation or not because I don't know what the PSI to MPA is. But do something like that, right? And it'll tell you how many scenarios it wants to run to evaluate that. And then you can run it. It is going to have to run the simulation, the study as you defined for every scenario you've defined. And it'll run additional ones if it doesn't find a convergent solution based off of the initial set. So this can take a very long time to process and get results out of, especially as your assemblies get more complicated. And if you add a lot of additional constraints. I used a single variable, a single constraint, and a single goal. You can have 5 variables and 5 constraints. Your number of scenarios that's going to run for that is going to be huge, but you can set all those things up, hit run, come to campus, go to all your classes, and then come home, and maybe it would be done running by the time you got back, depending on how many set points you set, right? Yeah, so the sensors become the constraints. So you add the sensor, and that says, I want to measure this as a constraint. And then after you've added the sensor, you specify what the constraint bounds are, right? So in mine, I said the stress had to be less than 1,000 PSI. I'll stop it and go back to that so you can see where. So the sensor type, I usually use a simulation result. So I'll hit stop. It's got to finish doing, but you can go through and you can put whatever you want. Most of the time, you're going to want to define a simulation before you do the optimization, and then use something from the simulation to run your set. But if your goal is just to minimize mass or something, you don't care about the strength properties of the material, you can just run an optimization that minimizes mass, right? So again, this is just trying to visualize this and get finished. If I go to my variable view, I can edit all these things. It failed. It's because I didn't use the right value. So the maximum stress inside the part was 51,000 PSI, and I put 1,000 PSI as the goal, so it could never achieve that. But yeah, you can add as many constraints here. Just do add sensor. Most of the time, I'm using simulation data, and then stress is the most common result there. But you could also use displacement, frequency, velocity. Now, if you're not running a thermal study, then that's not going to work, right? So if I try here and say thermal, right? Value, data not available, because I don't have a thermal analysis defined for this part. But if I do stress, and it says, hey, this is the current value, which if I had looked at that, I could have pulled out, right? Make sense? Somewhat, hopefully. All right. Well, that's time for today. Again, on Friday, you guys have your mini projects, part 1. Your Rube Goldberg projects are due. So make sure you have that. Your submission for today should be your assembly file from this set up. I put some constraints on there as to show specific part combinations. I wanted to show you guys you can hide and show components. So if you're not showing those specific components, that's fine. And I want you to see that you have some simulation results. So if you have the assembly file with the simulation results, that's good. And the part file from Monday with the simulation results, put all of that into one zip and submit that. The simulations results do generate a bunch of extra files. So you'll notice there's all these extra files. I do need those to see the simulation. So when you're going to submit it, just take the folder that you have all your stuff in, send that to a zip file, and then submit that zip file. So that way I have all your simulation results built in with it. And whenever you're sending people SolidWorks simulation stuff, you should do that anyways. Questions in the last minute of class time here? All right, well, I'll stick around and answer any questions you guys have individually.